Whenever we talk about how good an AI model is, we almost always hear just one number, its accuracy. But what if I told you that single score is often just a tiny, and sometimes a really misleading part of the story? Okay, let's just jump right in with a question. You see a headline, an AI model is 95% accurate. Is that a good model? I mean, on the surface, that sounds amazing, right? It's like an A+ score in school. But is it actually doing the job it's supposed to do? Well, the answer, and this might surprise you, is not always. In fact, that 95% accurate model could be completely, totally useless. This is a classic idea in machine learning called the accuracy paradox. And really getting your head around it is the key to truly understanding how AI performs. So let's pull back the curtain on this 95% accuracy illusion. We're going to see exactly why that one shiny number, all by itself, could be so incredibly deceptive.
To make this super clear, we're going to use a perfect, real-world example pretty much everyone gets, building a model that filters junk emails out of your inbox.
So this chart shows a really common situation. Think about your own inbox. The vast majority of your emails, let's say 95% of them, are legitimate, right? They're not spam. And only a tiny little fraction, maybe 5%, is actual junk. This is what we call an imbalanced dataset. And it's the exact kind of scenario where just looking at accuracy starts to fall apart.
All right, now imagine we build a super lazy model. I mean, it's the laziest model in the world. Its one and only rule is to just stamp not spam on every single email that comes through. It doesn't even bother to look at the email's content. It just gives the same label over and over again.
And boom! This is where the paradox just smacks you in the face. Because 95% of the emails are actually not spam, our lazy model is right 95% of the time. It gets that fantastic A+ accuracy score, but it has completely 100% failed at its main job, which was finding spam. It's totally useless, but its score looks amazing.
So clearly, we need a better tool. To get past this whole accuracy illusion, data scientists use this really powerful visual called a confusion matrix. It lets us see exactly what a model is getting right and, way more importantly, what it's getting wrong. So what is this thing? Well, at its heart, a confusion matrix is just a simple table. But its real power is in how it organizes the 4 possible things that can happen with any prediction. It's really the fundamental tool for getting beyond that one accuracy number and understanding how a model actually behaves. So check this out. This is how it's laid out. The rows show the actual truth. Was the email really spam, or was it not? The columns show what our model predicted. This simple little grid gives us a home for every single prediction, sorting each one into 4 very distinct categories.
All right, let's break down what these 4 boxes actually mean, using our spam example. A true positive? That's a win. We caught a spam email. A true negative is also a win. We correctly let a good email through. Now, the errors, that's where it gets interesting. A false positive is a false alarm. That's when an important email gets thrown into your spam folder by mistake. And a false negative is a miss case. That's when a piece of spam slips right past the filter and into your main inbox.
Okay, so now that we've got the lingo down from the confusion matrix, we can actually calculate 2 much more insightful metrics. These give us the nuance that accuracy just completely lacks. They're called precision and recall.
And this right here, this is the big trade-off you always have to think about. Precision answers the question of all the emails we called spam, how many of them actually were spam? It's all about confidence. It's about minimizing those false alarms. But recall asks a totally different question. Of all the spam that actually existed in the inbox, how much of it did our model successfully catch? This one's all about completeness, about minimizing the things you miss.
So let's go back to our spam example, but this time, let's use a model that's actually trying to find spam, and let's evaluate it using these new, smarter metrics.
Okay, so this model has a precision of 50%. What does that actually mean? Well, it means that when this model flags an email and says, hey, this is spam, it's only right half the time. The other 50% of the time, it's a false positive. It's flagging a perfectly good email.
But then, look at this. Its recall is 100%. What does that tell us? It means this model successfully found every single piece of spam in the entire dataset. It didn't let a single one slip through. See, you can already start to feel the tension between these 2 numbers.
So which one do you care about more? It completely depends on the cost of being wrong in your situation. You need high precision when a false alarm would be a disaster, like marking a critical job offer email as spam. But you need higher recall when missing something is the disaster, like a medical test failing to detect a disease.
In that case, you would much rather have a few false alarms than miss a critical diagnosis, right?
And hey, this whole trade-off between precision and recall, it doesn't just apply to simple yes or no problems. It scales up perfectly to situations where you have lots of possible categories, what we call multi-class problems.
So for a problem like, say, classifying news articles, you might want one single score to tell you how well you're doing across all the categories, like sports, politics, tech, and so on. To get that, we just average the scores. Macro averaging treats every category equally, even the rare ones. Micro-averaging, on the other hand, treats every single article prediction equally, which gives more weight to the bigger categories.
And here's a really cool little technical insight from the source material. When you're dealing with a multi-class problem, the micro-average precision and the micro-average recall will always be the exact same number. And get this, that number is also identical to the overall accuracy. It's just a great little reminder of how all these metrics are mathematically tied together. Okay, let's bring all this home now and turn it into a final, actionable takeaway. Because the real skill isn't just about calculating these numbers, it's about choosing which one to focus on in the first place. Here's a super simple but really powerful framework you can use. First, always check if your data is imbalanced. Second, you have to clearly define the real-world cost of a false alarm versus a missed case. And third, remember that you can often tune a model sensitivity, kind of like a dial, to find that perfect balance between precision and recall for your specific goal. And that's really the bottom line here. The best way to measure an AI model isn't some technical question that has one right answer. It's a strategic choice, and it's based entirely on what you're trying to achieve and the specific cost of being wrong in your world.
So I'll leave you with this final thought. The next time you see a headline about some AI with 99% accuracy, or you find yourself looking at a model's performance report, what's the very first question you're going to ask? Because now you know the true story is never, ever just about that one single number.